Okay. Hello, everyone. Today I'm going to present a new project what I've been working on for past several weeks. It's called EMQTTB, or EMQTT bench daemon. So first of all, I'm going to describe why we chose to work on this project. And there were two reasons. First of all, we gathered some experience with the old MQTT bench script during our 100 million connections test. And I was listening to what Thales was saying on the meetings while performing this test, and I identified some areas for improvements. So how did this test go? We provisioned tons of AWS instances, quite expensive ones, started shooting traffic with MQTT bench. Then we find out that the rate is too high, for example, and either the bench daemons or the MQTT or the EMQX, they stop responding because the load is too high or they run out of memory. And the test has to be started all over again and repeat this loop again and again, which is very time consuming for the engineer who is running this test, and also quite expensive because we run these very expensive AWS instances. So something should be improved in how we do more tests. And the idea what I had is, why don't we adjust, for example, publishing rate or connection rate automatically? Also, the second improvement what can be done is we need metrics from the load generator, so we can keep an eye on what is it doing, because the old MQTT bench script, we only know that it overloaded the target or it overloaded the load gen when you start seeing error messages in the console. So the feedback loop is not very good with it. Another reason why I chose to start working on this new load gen is persistent session feature that I've been working on. The testing of the persistent session is quite complicated. You need to give the database a good load by switching between producing the data, which causes the data to be written to the database, and consuming this data from the database. And doing this with the old MQTT bench script is quite finicky. So another reason to create this MQTTB project was should be scriptable. So should support complicated login scenarios. So hopefully this explains the reasoning behind this WAL project. So now I will just speak about the architecture that I chose to solve these problems. Let's talk about the core concepts of EMQTTB. First of all, we have worker. A worker is a process that corresponds to a single MQTT client. The worker runs a behavior, and behavior is a callback model that defines what does the worker do. The behavior has an init callback and handle message callback. So, for example, if you want to implement a message loop, you can do this. The worker in MQTTB is implemented in such a way to consume as little memory as possible. And I think I achieved this goal pretty well because basically the worker takes as little memory as an OR1 process that does not do anything, pretty much. Because everything, every data that worker has, it is either shared and stored in the persistent term. So, so basically, it does not have to be stored in the process heap, or the worker stores it in the process group leader, which is already present for every OR1 process. So basically, a worker consumes 0 extra memory, which hopefully makes it our load tests more cheap because we can spawn more workers in the same in the same AWS instance. Okay, the next concept is the group. And group is a group of workers with the same behavior and with the same configuration. The next concept is scenario. And scenario is a script that creates possibly multiple worker groups. It controls the number of workers in each group, and it can switch stages. Stages are just arbitrary. For example, there can be stages to connect clients, to run traffic, disconnect clients, what have you. Also, behaviors, they can read the current stage if necessary and change their behavior based on it. The coolest feature is autorate. Autorate is a function that adjusts the values used in the login automatically based on some metrics. For example, the available CPU load, or as I will demonstrate later, on the latency of requests. Also, there is auto-scale feature that uses autorate to determine how fast the group scales, which is again can be used to prevent overload. So if MQTTB detects that connections are not being accepted by the MQX, it can slow down the connection rate. So we can avoid overloading the EMQX, and it's done automatically. Also, this new load gen, it has REST API. Right now, it's not very complicated. It has a health check endpoint. It has metrics endpoint, where Prometheus can scrape the current metrics. Yeah, speaking of metrics, it also supports push gateway. It has a REST API to get the current running stage. And quite interestingly, it can reward the configuration in the runtime. And this configuration will be applied automatically. Has a bunch of CLI arguments. This help document is generated automatically from the configuration schema. Also, we have manual pages, and we have HTML documentation for all the parameters. Okay, let's move to, I will just demonstrate how the scenarios and how the behaviors look like. Let's take a look at the pub scenario, which emulates pub argument from EMQTT bench, the old script. So this is the Orwang file. It has a scenario behavior. And it exports 3 callbacks: name, model, and run. Name is quite simple. It translates module name to a human readable name, like pub. The model is more interesting. It describes all the configuration parameters used for this scenario. For example, topic, to publish messages to, you can define which CLI operand is used, which short CLI operand is used to read the topic. So basically, this schema is very similar to what is read by MQTT bench script. It's just more declarative, so to speak. And the run callback is the most interesting one. So we read configuration, and we start a worker group, like shown here, with behavior pub. When we set the interval for connecting the clients, we set the ramp up stage, and we set the target for the group. The target is a concept that specifies how many clients you want to be maintained. So if a clients are stopped or they crash for some reason, the group will try to respawn them automatically to maintain the set target. Also, when the group is scaling, it uses the interval to pause between spawning the clients. And this interval is automatically adjusted if you configure it to keep the connection latency constant. Then we set stage, run traffic, and then we just wait the specified time while running traffic. Then we set the scenario to complete and we stop it. In a similar fashion, we implement scenario sub. It also has the schema. It also has the run callback with stages and so on. Let's take a look at some of the behaviors. And by the way, you can absolutely create your own scenarios and your own behaviors. So the pub behavior, it has init per group callback, which creates the shared configuration. Because remember that we want to share as much as data as possible between the workers to avoid storing any data in the heap. So we create some metrics. We create number of published metrics, number of published messages metric, which can be observed in Grafana. We create an auto rate. It's a special process that keeps track on the latency. So let's take a look at how it calculates the optimal interval between publishing the messages. So every so often it reads the rolling average of publishing time and then it compares it with the expected latency, which we set here in the beginning. So this is how we try to adjust the optimal publishing rate in the runtime. Then this init callback is called for each worker, and for publishing worker, the only thing that we store in the process heap is the PID of the connection process. And finally, there is handle message callback, which responds on the timer. And every so often we publish a message. We use instrumentation to calculate publishing latency. And we increase the counter for the published messages. Very simple. All right.
What's its timer for in the subscriber?
It's the publisher, and this timer is used to trigger the events when we publish new messages to the topic.
Okay. I thought you were still talking about the subscriber.
No, it's the publisher.
Okay, thanks.
Yeah, but subscriber is also implemented as a behavior, and it does not use any timers. It just handles the incoming MQTT messages.
Okay, cool. Thanks.
Yeah, so of course you can implement your own behaviors and your own scenarios. But let's move on to the live demo. I hope nothing crashed because. All right, so I start the very basic pub scenario which emulates the old EMQTT bench script. So the CLI looks a bit different. First, we set a global argument push gateway to enable push gateway for Prometheus metrics. And when each command is prefixed with this @ symbol, so we run pub command to start pub scenario. It's a bit unusual, but it makes things quite a bit easier. So we set topic to foo and the interval for spawning the client to 1. And right now, auto rate and auto scaled are disabled. So everything runs at constant rate. Let's take a look at the metrics. In Grafana, we can see how many workers is there in each group, how fast the workers being spawned, how many messages published. Right now, nothing is being received, so this one is empty. And another important metrics for the user is the number of pending operations. Basically, every time the MQTTB starts any operation that has to do with sending a message to MQX, it increments a counter for this operation. Once it completes or fails, it decrements the counter for this operation. This way, we can monitor how many operations have been started but have not been completed. And if the counter for any operation skyrockets, we can know that we are overloading the login, the broker. And based on this counter, we can automatically adjust the rate, or we can simply see in advance that something is going on. And there's also latency. In a similar way, we can monitor if we are overloading the broker by looking at the latency for each operation. Also, auto rate is reported as a metric, but right now it is disabled, so it stays constant. Okay, this was a very simple scenario. Let's try to make it more interesting. Let's change the transport to WebSocket and enable SSL. Okay, as you can see, the metrics start growing, and the situation looks very much similar to what we see previously with plain socket connections. Also, notice that I changed water parameter. So instead of running the scenario infinitely, it only runs for 10 seconds. I guess it's useful if you just want to rerun the same scenario quickly. Notice that the way we specify the parameters for the client connection is quite different from what you see in MQTT bench. We use a separate command G to set these parameters. So we don't set it in the pub command. And this is useful because with G command, it creates a client configuration group, which can be shared between several scenarios, like I'm going to show now. So right now, I'm going to spawn two scenarios in parallel, which share the same configuration. So we will use WebSocket with SSL. Yeah, as you can see, two scenarios now running in parallel, and the received messages metric is now alive. So we started getting some messages. Yeah. So you can do this also. Another feature which I added for convenience is again flag. So, for example, if imagine you're load testing MQX while changing it, like you're tuning something inside, and you want to repeat the same scenario over and over again to see how you are improving the code. So to avoid typing this again and again, you can just run this again parameter, and MQTTB will restart the last command with exactly the same configuration. So imagine you're changing something, you tune in a parameter, you want to check how you're doing, you type again, and get a new result quickly. All right, let's check how autorate works. So in this scenario, we will start multiple clients which are going to start publishing messages to a topic with QoS2, and the initial interval for between the publishing events will be 0. And we want MQTTB to automatically adjust this interval so the latency keeps at 10 milliseconds. To enable autorate feature, we need to unlock the speed that it adjusts the control parameter at, because by default it's 0, so effectively it's disabled. All right, let's start it. We are going to see that we started to spawn the clients which start to produce messages, and the latency for publish operation starts to grow immediately. It grows to 20 milliseconds. And now the auto rate is alive. Sorry, I need to. Okay, this is better. Yeah, now you can see that average latency starts to decrease. Why is it so? That's because the auto rate started to automatically increase the interval between the published messages. So the interval between the published messages increases. It means the messages are generated less often, less vote on EMQX. So the latency decreases. And as you can see, it starts to be very close to 10 milliseconds, what we specified. So yeah, this autorate feature forks to minimize the error between the weighted parameter that we expect, in this case, the latency, and the rate. So it can be used for two purposes. For example, it can be used to avoid overloading the cluster. For example, we can start from a very small publishing rate, let's say 100 milliseconds, and then we can configure MQTTB to gradually increase, to adjust this rate so the latency stays, for example, at 10 milliseconds, like in this example. So we avoid overloading the broker. Also, it can be used to answer the questions. For example, what is the maximal rate where we can keep the certain parameter at certain value? Because sometimes the customers, they ask question, for example, okay, we want the CPU load at, let's say, below 10, and we want how many messages per second we can maintain at this hardware. So this autorate feature, it can answer this question very easily, because we can send, instead of setting target latency, we can send target CPU load, just start test, and it will, and the end rate will be the answer to a question. So no manual work is needed. Yeah, as you can see, tries best to maintain the set latency, and it's pretty successful at that. Of course, there is a little fluctuation just because my computer is running our stuff. Okay, let's stop it and show the last scenario called autoscale. So when we adjust the group scaling rate. In this case, we are going to take a look at how the number of workers per group speed is being adjusted as we hit. So basically, I configured MQX to stop accepting connections past certain interval, and now I deliberately overrun this maximum number in the test. So the connections start to be quite queuing up, as we can see in this graph. And thanks to autoscale feature, we started to increase the interval between the connection request. So it starts to grow. And we no longer spawn the clients at a crazy rate. So we still have pending operations, but it's not as severe as before. So now we avoid overloading the load gen by creating too many clients that cannot do anything. Yeah, as I mentioned, MQTTB has a lot of features, and so you can see it can be quite tricky to configure, but have quite good documentation where all the parameters are described. I'm still working on writing better descriptions for everything. But yeah, it is quite powerful, so hopefully it will improve how fast we can do load tests, what scenarios we can test. Yeah, that's it.